now. So we're beginning a new chapter. We did most of chapter, or we did all of chapter 4. No, we didn't do section 4.4. We did only part of chapter 5. We're going to revisit chapter 5 at the end of the year, actually. And we're going to do the last few sections in chapter 5 at the end of the year, right when we study rational functions. For now, we're going to jump to chapter 6, which begins the concept of radicals and square roots and cube roots. And this will lead us into the next section, which goes into the quadratic formula and solving for imaginary numbers and such. So we're going to see how this is a lead into that. But before we can do that, what we want to do is discuss what roots of real numbers are and then determine some correlations that exist amongst those roots. So again, we're going to talk about what a square root is really defined as. So a square root is the solution to this equation, really. That's what it is. If you think about it, how would you get x by itself? You would take the square root of both sides to get rid of a square. And you learn some of this when you're in your 8th grade math class. You learn about square roots and powers. And what's happening here really, and this is what's a little bit intriguing to see, and most people don't seem to notice this right away, is that if you had this, which is what we have, we would say, okay, square root, and you get x equals radical b, but we get two answers out in front. And the solutions to this equation are known as plus or minus radical b. And that's what we see above in that sentence. Why are there two solutions to this equation?
Because you're going to get the same thing square and negative times 2.
Correct. So imagine b was 9. Imagine if b in this equation was 9. What squared gives you 9? 3 or? Good. So either of those answers work. Now, this is when you solve an equation. You get the two roots to the equation. We're going to see later when it says to simplify an expression, we're going to talk about something called the principal square root. And the principal square root is usually used in real life. Like if somebody is looking at geometry and they want to find the length of the hypotenuse, it's a squared plus b squared equals c squared. So you have to take a square root to get c by itself. So as a result, you're not going to look at a negative length. It doesn't make much sense. So you usually use what's called the principal square root. And the way this graph looks, let me just show you a quick graph of this. It's like a parabola on its side. And we haven't even really looked into parabolas yet, but some of you have seen it before. A parabola is usually this. Okay, that's what a parabola usually is in the bottom left down here. But the square root function looks like this. And this is showing both legs of the square root function. This is y equals radical x. This is y equals negative radical x. So remember how we had this plus or minus symbol here? The principal square root in math is termed as like the positive square root. And that's representative from this, or represented by this function up here. Now, if you try to put the vertical line test to this, is it going to be considered a function? Why not? When does the vertical line test fail? What occurs to fail?
When there are 2 points in like one line.
Yeah, so when you put the line through, when there's more than one intersection. So I put a vertical line through, and there's an intersection here and here, both of those spots. So when discussing functions and looking at radical functions, if the negative part doesn't matter, usually you'll see a graph of just y equals radical x. You don't always see the negative radical x there. So this part up here is known as the principal square root, the positive values that we were looking at. Okay, all those positive values there. Let's see. If you were told that b, the value of b were negative, such as this, okay? X squared equals negative 7 instead of positive 9, like we had a minute ago. What would the solutions to this be? What numbers multiply by themselves to give you negative 7?
Like no real number?
Yeah, there's no real number that will do this. Why not, Kelly?
Because if you square something, it can't equal a negative number.
Yeah, whenever you square something, you can't have a negative answer. And that's what Niall was alluding to before, that because we square it, it becomes positive. So if you have an equation like this where there's an x squared and equals a negative term, we're going to introduce this in the next maybe 3 or 4 sections as an imaginary number. So for now, though, you would just say there's no real solution. Okay? No real solution. So an equation like this has no real solution. Anything else I wanted to discuss here? No, let's go to an example. In the first example, we just want to simplify these three expressions here. Okay? When you're simplifying something, when you're not solving an equation, write this down, please. When simplifying an expression, you're only giving the answer of the principal square root. When simplifying an expression with a radical, not an equation, an expression, you're only giving the principal square root. So what's the square root of 4? Only the principal square root of 4? Thank you. Okay, just 2. Again, if you had x squared equals 4, you would take the square root and say plus or minus 2. Okay, but here we have just 2. We're looking at the principal square root. So the negative is outside of the square root, so we think of it like this. We take the principal square root of 16, which is 4, and we apply the negative sign to it, so yes, it's negative 4. We're still finding the principal square root for part B, but there was a negative or an opposite sign out front. My teacher used to tell me, think of it as an opposite sign. For part B, it's saying the opposite of radical 16, which is the opposite of 4, and the opposite of 4 is negative 4. And then the last one is what? What's the last one, Niall? 3/5. Okay? How do you know that's true, Niall? What can you do with a radical with a rational function or rational expression inside of it?
Split it off to get that 9 and radical 25.
Good. You can do radical 9 and radical 25, splitting it up. Use that same concept in a minute, or actually in this and the next lesson, with multiplication also. All right, with multiplication as well. 2. Find the real roots of each equation now. Find the real roots. So now you're going to have how many answers? 2 answers. You also know that's true because you see it's x squared. When you see an equation with a squared term, you need 2 answers. Now those answers could be both imaginary or they could be both real. And we'll see how in later sections imaginary answers come in pairs. So in this case, you can't have one real and one imaginary. Either they're both going to be real or they're both going to be imaginary. So how about part A to start? Part A is the easier one. What do you got for part A? What would be your answers for this one? Ben, what do you got? Yeah. Take the square root of both sides. X is plus or minus 5. Agreed. How else could you have solved that one? Think about factoring like we've done. Couldn't you have moved the 25 over? Side note, okay? You could have written it like this, by subtracting 25. See how it's on the right-hand side? I move it over the left. What does this factor into? What does this factor into? It's difference of 2 squares. What are the squares?
X minus 5 and x plus 5.
Very good. And then if you solve this, what would your answers be? And isn't that what we got a little bit ago? Take a look back up here. We said the answers to this by taking a square root of plus or minus 5. Same answers as if you had factored this. So difference of squares corresponds directly to the square root function that we're going to be looking at. Is that clear? So difference of squares is exactly related to that. This is plus or minus 5. This is plus or minus 5. Same thing. Part B. Part B. What you got? Can you factor x squared plus 49? Is that factorable? Is x squared plus 49 factorable? Now it's a plus sign in the middle though. So if you wrote x plus 7, right? Like that. You're saying factor into x plus 7, x plus 7. If you FOIL that out, you're going to get x squared plus 14x plus 49. It's not what we have though here, right? There's no middle term. There's no middle term here. Could you factor this one?
No.
Why not?
If you subtract it, you get the radical is negative 49 versus the imaginary.
Yeah. So remember how a minute ago we were saying, if you try to square root this, you're going to get x equals square root of negative 49. Well, plus or minus, really. But the problem is that when you have a negative under the radical, it's not real. Okay, so no real solutions. So it'd be an empty set in the real number set. Okay, there's no real solutions here because there's no number when squared that gives you negative 49. Only 7 times negative 7. Or 49 times negative 1. Or negative 1 times 49. But there's no number that's the same that multiplies to give you negative 49. Okay, that also comes about because this, to be factored, you'd have to have a middle term there. You'd be missing the 14x in the middle. How about part C? There are 2 ways to solve part C. There are 2 ways to solve it. Go ahead, Kelly.
I got x equals the square root of 5.
Square root of 5. How do you do it? Go ahead.
Well, first you put the 20 on the other side by adding it, and then you get 4x squared equals 20, and then you divide by 4, and then you get x squared equals 5. And I'm pretty sure the number is like just really, really long. So it's just going to be plus or minus square root of 5.
What's the word for a number that's really, really long?
Irrational.
This is irrational, good in this case. Irrational. Now, you could have numbers that repeat, that are rational, that are really long also, but this is a non-terminating, non-repeating decimal. Okay? And she's absolutely right. It's radical 5. Now, you want to see that solved with difference of squares, you can do that also. So let me just give you a quick preview of that. What could be factored out of this? What number could be factored out if you're doing factoring methods?
2x.
Oh, but 20 is going to be the problem, right? But my question is, what's the GCF? Well, what's the GCF? 4. Making this x squared minus 5 like that. Agreed? Now, this is going to blow some of your minds. Others might just be like, what the heck did he just do? So if it doesn't work mentally for you right now, don't worry. You don't have to do it this way, but you could write it like this. And try to make sense of what I just wrote. Think back to over here. When this was a 25, didn't you take the square root of it and put it here and here? Isn't the square root of 25 just 5? And didn't that go right here and right here? Well, what's the square root of 5? It's just radical 5. So if you put that there and there, and you solve this one, make a t-chart, you get x plus root 5 equals 0. You get x minus root 5 equals 0, giving you x equals root 5 when you add it over, and x equals negative root 5 when you subtract it over. Still giving you the same exact answers as up here, plus or minus radical 5, plus or minus radical 5. So difference of squares, believe it or not, technically speaking, doesn't have to be a perfect square in both spots. Do you see what I'm saying? If you ever have a difference, if you had a difference like this, and this is where I'm saying it's a little bit weird. If you had like x to the 4th minus 17. This is x squared plus root 17, x squared minus root 17. Then you could try to factor this as difference of squares. You could write this, and this is going to get even more weird now, as x plus root 17, x minus root 17. And on the right-hand side, this cannot be factored. So technically speaking, whenever you have a difference and you want to factor it, you can just take the square root of each term. The square root of the square root of 17 is a double square root. You just take the square root and then take the square root of that answer afterward. So whenever there's a difference with a variable and it's just a binomial, technically speaking, you could factor using difference of squares. If they're not perfect squares, though, it comes out as messy answers, so you usually don't see that very often. Okay, but just to give you a little, side note, because you might use that in calculus. Use that when you're rationalizing binomial denominators and such. When you have like x plus radical 7 or something. Okay, you have to keep that idea in mind. If we look at this next idea, we're going to talk about something called the cube root. And the cube root is analogous to the square root. The square root was the solution to the equation x squared equals b. Well, the cube root is a solution to the equation x cubed equals b. Hence cube root, because it's x cubed. So what you're trying to think about now is what number times itself will give you whatever b is. And that's denoted by a cube root. So think about this for a second. What's the answer? What number? 2. Because 2 times 2 times 2 is 8. We all agree with that? So therefore, if I were to solve this, it would look like this. That's really what it is. You cube root both sides. You cube root both sides. Now, if I cube root, you need to look up to understand this. If I cube root and this 3 appears here, then when I square rooted, what was really there? Even though we didn't show it, what was really here technically? A 2. This is called, write this down, actually it's on the next slide. I think is it the next slide? It's the slide after that. But this is called the index. The index. So the 3 indicates we're solving something that was x cubed. Or we're looking for a number when multiplied by itself 3 times. Right? 3 times gives you 8. 2 times 2 times 2 gives you 8. So this 3 indicates the frequency of which it's multiplied. So if you multiply a number like 2 times 2 times 2 times 2, that's 2 to the 4th, right? And that's 16. So the 4th root of 16 is really just 2. So the index indicates how many times the number is multiplied by itself. So what you're really doing, hold on Kelly, I see your hand. What you're really doing is you're thinking like this. You're thinking that this is really cube root of, and your question is fill in the blank. That's what it's really saying. What number times itself, written 3 times, gives you 8? Well, it's 2 times 2 times 2. If I can write something like this, this is really 2 to the 3rd, isn't it? 2 times 2 times 2 is really 2 to the 3rd. So really this is this now. I can think of it this way. And a cube root and a cube cancel each other out, giving you again just 2 as an answer. Just showing you where this comes from. You need to think of when you see a cube, fill in 3 blanks. If those blanks fill in with a certain number you can find, then that is a perfect cube.
I just want to know, the index is just a 3, right?
Correct. The 3 itself, right here, is the index. That little number written above the radical left side of it. So let's look at some examples to understand this. Simplifying these 4. Cube root of 27. What number times itself, Paul? 3. Because I think of this as, remember, blank, blank, blank. 3 by 3 by 3 is 27. So this is really this, which is really this. Part B. Part B. Luca.
-2.
-2. Now here, you can have negatives. You can, because a negative times a negative times a negative. My handwriting's off on. A negative times a negative times a negative is still a negative. Why is this, the stylus is dying and it keeps like flapping over? So you see that -2 times itself 3 times gives you -8. So this is really this. And a cube root cancel, so it's really just -2. How about part C? Part C is a little bit tricky. Think of part C as breaking it into 3 things like we're doing in the previous lines. What times what times what will give you 10 to the 6th power, Niall? 10 squared. And this is where you need to know your laws of exponents. I'll do part D down here. This is part C up here. So this is really 10 squared, 10 squared, 10 squared. Because 10 squared times 10 squared times 10 squared, what do you do to the exponents? You add the exponents. So this is really the cube root of 10 squared cubed. Right? It's 10 squared, 10 squared, 10 squared. That's 10 squared cubed. The cube root and the cube cancel, giving you just 10 squared as an answer. Or 100. Again, the cube root and the cube cancel, leaving behind 10 squared, which is really 100. So technically speaking, I can take my exponent, see the 6? Look at the original for part C. See the 6? I could take the exponent and divide it by what number to give me the answer here? The exponent is 6, divided by what number gives me this right here? The index. Write that down. Write that down. You can take the exponent under the radical and divide it by the index. Sometimes it won't divide evenly, and we'll talk about that. And that will come up again. We'll talk how that works. But you can divide the exponent by the index, really. So that helps us for part D clearly. Give me the answer for part D real quick, and then we'll go through how it works. So part D was cube root of D to the 12th power. What's the answer? Just quick answer.
D to the fourth.
D to the 4th, because Kelly said 12 over 3 is 4. How do I know? Here's how I know. That's what this really is. D to the 12th is really D to the 4th, D to the 4th, D to the 4th. And that, in essence, is really D to the 4th cubed, all under a cube root, which gets you back to the answer that we got. So either you can take the exponent divided by the index if it divides evenly, or you can write it out like this and show that that works. That make sense so far? Okay, what do you got on the bell today, Ryan?
12.
12? So we're going to quickly just define things. We've already talked about what the index is. Okay, see n, the nth root of something is the solution to the equation x to the n power. So if I had x to the 5th power equals 32, I would say, well, x is really the 5th root of 32. What's the 5th root of 32? Come on, somebody's got to be able to do that. 5th root of 32. 2. Think about it. Use process of elimination. If you do 3 to the 5th, that number is going to be much larger than 32. Because 3 to the 3rd was 27. 3 to the 4th? Nobody? 3 to the 4th? 81. 3 to the 5th? One thing you can do is go through your powers. Look at like 1, 2, 3, and 4. And look at the first few powers of each of those. Try to get those in the back of your head. It might help just to have them memorized. You could always use a calculator, but just to know them.
243.
243, very good. Okay, you can go through these. Powers of 2 you should really know, because computers always work that way. Ever see the size of like the RAM, or it used to be at least before we had gigs of RAM? It used to be like 128 megabytes. Then it was 256. Then it was 512. Then it was a gig, which is really 1024 megabytes. So it was always powers of 2 for a long time. So powers of 2 still occur a lot. It's good to know your powers of 2. All right? So it doesn't matter what the exponent is. The exponent here, again, this exponent could be 7. And then the answer is the 7th root of 32. That might not be an exact value though, right? The 7th root of 32 is not going to be. It's going to be a decimal value. You'll see how to solve those actually next year with logarithms when you're in Ms. Coop's class. You're going to do algebra for the 4th quarter in that class. All right, so let's simplify these. 4th root of negative 16. Can you find a number when multiplied by itself, remember 4 times, that's what this really means, to give you negative 16?
No,
Why not?
because
What's the 4th root of positive 16? What's the 4th root of positive 16? 2. And if you make it negative 2, is it going to work? If you multiply negative 2 times itself 4 times, does it come out to be what kind of a number? A positive number. So write this down. Write this down. Whenever the index is even, the radicand cannot be negative or must be greater than or equal to 0. Again, when the index is even, the radicand must be greater than or equal to 0, or just cannot be negative. And if you went to x to the 6th power, you would pick up on the trend obviously even more, but I'm trying to give you guys a quick synopsis of that. How about part B? So again, part A, there's no real solution. That's where we would start using imaginary numbers, but we haven't gotten there yet. Part B, the 5th root, I already just did this one a minute ago. It's just 2. Okay, how do I know that? Because 2 times 2 is 4, times 2 is 8, times 2 is 16, times another 2 is 32. Keep track with your fingers. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So 5th power of 2 is 32. Part C. Part C. X to the 5th. Niall knows that because he remembers his rule. Take the exponent divided by the index. 20 divided by 4 is 5. Or maybe he said to himself, what's the 4th root of something written 4 times? Well, that would be x to the 5th, x to the 5th, x to the 5th, x to the 5th, which is really x to the 20th. So therefore, his answer is indeed x to the 5th to the 4th, but under a 4th root, which is just x to the 5th. Okay, same answer. Either by looking at it or by doing it. And the last one, the fifth root of -1. -1. So what can we write down as another statement? We wrote down about even indices. What else can we write?
If it's odd, it has to be a negative.
Now it has to be.
It could be negative or positive.
So if the index is odd, so this answer by the way is -1. If the index is odd, the radicand can be any real number. If the index is odd, the radicand can be any or all real numbers. We only have a minute left. I can do part A very easily, and you can use part B to help you from part A. Part A says, determine the value of x so that the expression represents a real number. Well, the index, when there's nothing there, is really a, Will said it earlier. If we're looking at a square root, what's the index really? It's really a 2. That index is even. So we know that the radicand has to be positive, right? So in part A, you can set the radicand greater than or equal to 0, and then solve by adding 3. So determine the values of x. Any greater than or equal to 3 is part A. But for part B, when you do this, you set the radicand greater than or equal to 0. It's a quadratic inequality. You need to use the number line test with the critical points that we learned about. Alright, so finish up part B on your own. You can either watch the video or look at my notes and do it. Over break, 6-1 homework. Okay, and then come up with those 3 questions. I'll send you instructions for those 3 questions. Alright, if you want your quizzes real quick, you want to see your grade, put them in the grade book.